What if I told you the secret to making stronger, more sustainable buildings was hiding in something we usually just throw away? Today, we're digging into a really fascinating material called rice husk ash, or RHA for short, and finding out how this simple farm waste could be a total game changer for construction.
Yeah, I know. It sounds a little too good to be true, doesn't it? I mean, can something we consider garbage actually make the concrete that builds our world even better? Well, that's the big question we're tackling in this explainer. We're going to play detective and follow the scientific clues to solve this mystery.
All right, so let's get right into it. What exactly is rice husk ash? Well, it's pretty simple. You know the little protective shells around grains of rice, the husks? This is the ash that's left over when those husks are burned. For a long, long time, this stuff was just waste. But then scientists started to realize it has some pretty incredible properties.
But here's the thing, not all ash is created equal. For RHA to actually work in cement, four things really matter. First, there's the silica content. Think of that as the magic ingredient. Then there's its chemical structure, which determines how reactive it is. Third is fineness. Basically, the smaller the particles, the faster they work. And finally, something called loss on ignition, which is just the amount of unburnt carbon left over, kind of like gunk that can get in the way. These are the four big clues we're going to track.
So to figure out what makes the best RHA, the source material we're looking at put four different types head to head. Let's meet our contenders. We'll just call them A, B, C, and D. Each one is a little different, and by comparing them, we can figure out what really makes a difference. Okay, first up, let's look at the physical stats, the tail of the tape, if you will. And right away, something should jump out at you. Just look at the particle size. Contenders C and D are way, way finer than A and B. They've got much smaller particles, which means a lot more surface area. Just, tuck that little fact away for later, because it's going to be a big deal. Now, let's check out the chemical profiles. On paper, RHAD looks like an absolute champion. It has the most silica and super low unburned carbon. That's the LOI. But then you look at RHAC. Whoa. Its silica is the lowest of the bunch, and its LOI is a massive 11.35%. Now, that much unburned carbon is usually considered a huge flaw. So right off the bat, RHAC is our underdog. So we've got our four contenders, each with its own story. Now it's time for the main event, the test. Let's see how they actually perform when you mix them into mortar and ask them to do their job. The test measures something called pozzolanic activity. Now that sounds super technical, but it's really not. It's just the key chemical reaction that lets this stuff bond together and get hard and strong, just like cement. The bottom line is simple. The higher the pozzolanic activity, the better it performs. And the results are in. And this is just wild. RHA and B, their performance is kind of variable. But look at C and D. They absolutely blew the doors off this thing. And get this, RHAC, our underdog, the one with all that carbon we thought would be a problem, it's actually the most reactive of all of them. How on earth is that possible? This chart really tells the story. I mean, it's not even close, is it? C and D are playing a completely different sport than A and B. So our top two performers are the ones with the finest particles. But one of them has what's supposed to be a fatal flaw. This is getting really interesting. And this is the real heart of the mystery, right here. Everything we thought we knew suggested RHA should have been a terrible performer because of that high carbon. But it wasn't. It came out on top. There has to be something else going on, some secret ingredient that we haven't found yet. As it turns out, the next clue comes from the origin story of our contenders. It turns out that our two winners, C and D, have a very close relationship. In fact, one is literally made from the other. Okay, here's the big reveal. RHAD is just RHAC after it's been put back in the furnace for another 6 hours. That's it. This simple extra step takes the already high-performing but flawed RHAC and refines it into the super-powered RHAD. And you can see that amazing transformation right here, side by side. That second burn gets rid of almost all the extra carbon, making the LOI just plummet from over 11% down to about 1.6%. At the same time, it makes the active silica more concentrated and the particles even finer. It literally takes something good and makes it great. But wait a second, this still doesn't fully explain why RHAC was so good in the first place. We're still missing the final, most important piece of the puzzle. It's not about how much silica there is, but about its form.
You see, silica basically comes in two flavors. There's crystalline silica. Think of it like a box of uncooked spaghetti. All the strands are straight, rigid, and neatly organized. Then there's amorphous silica. That's more like a bowl of cooked spaghetti, all tangled up, messy, and ready to stick to everything. And that tangled, messy structure is precisely what makes it so highly reactive.
And bingo, this is it, the final clue that solves the whole case. X-ray tests show that RHA A and B are full of that neat, orderly but less reactive crystalline silica. But C and D? They are absolutely jam-packed with the messy, tangled, super reactive amorphous kind. That was the secret ingredient all along. That's why they perform so well.
So, when you put all the clues together, the verdict is clear. The secret to RHA's strength isn't just one thing. The number one most important factor is having lots of that reactive cooked spaghetti amorphous silica. Having superfine particles also gives it a major boost. And as our underdog RHAC proved, if your silica is reactive enough, you can even overcome a pretty serious flaw like high carbon content.
You know, the researchers themselves really summed it up perfectly. They said it's not about the total amount of silica you have. It's about the amount of the right kind of silica. That amorphous structure is what truly unlocks the incredible potential of this material. This whole investigation into rice husk ash is just incredible. It really shows that amazing value can be hidden in the things we just discard every day. And it makes you wonder, doesn't it? What other scientific secrets, what other powerful supermaterials are just sitting out there in our waste streams waiting to be discovered?